All right, howdy folks. Welcome back to Professor Carbon. In this video, we're going to talk about the concept of aromaticity and how the Lambert lab has been able to take advantage of some of those concepts to generate some organic molecules that have truly exceptional properties. And so the first one of these is the molecule shown here. This molecule was first published in 2016 in a publication in Nature. And what's really exciting about this molecule is it's an organic OH bond that has the same kind of acidity as HCl. And so that's crazy acidic for an organic OH. And my questions for you are kind of outlined up here. And really what I'm getting at is why. How can they generate an organic OH that is so acidic that it can be used to generate, pKa's close to HCl, which is a very strong acid? And so what I'll ask you to do is first to consider the structure of the conjugate acid or base. By the way, there's a second molecule down here that might not be visible. The bottom one is a base, the top one is an acid. So the same concept works in both directions. So please just draw the conjugate anion of either that acid or base. Then clearly draw the resonance hybrid or some resonance structures to explain it. And then let's see if we can come up with a rationale. So like with all of these videos, if you want access to the PDF, you can download those on our Patreon page. And I really encourage you to actually take a pause and work through these videos all on your own before you just listen to me give you the answer. So please go ahead and click pause now and try to attempt this one all on your own. All right, welcome back. Hopefully you have a great explanation for how we can have such strong organic acids and bases. And the first step of this here is just to pretend that we're going to remove H+, and let's just consider the stability or structure then of the conjugate base. So that would be this anion. And often, remember when we're discussing pKa's and acidity and basicity, what we're really trying to ask is how stable is that cation or anion? And in this case, we're talking about an anion stability. And the anion can be stabilized a number of different ways. So probably the most significant is what kind of element is that charge on? And as a reminder, that correlates with electronegativity. So carbanions, those with carbon, are typically less stable than those with nitrogen, which are less stable than those with oxygen. And that kind of correlates with electronegativity. Kind of the second most significant thing is resonance. And so the number of different resonance structures you can draw, as well as the structure and stability of those resonance structures, really tells you a lot about how stable that anion should be. Lastly, we can talk about things like inductive effects, but often inductive effects are the weakest of the three effects that can contribute to acidity and basicity. So recognizing that, let's just start drawing some resonance structures here. And I'm going to be better about drawing So now we have moved that negative charge into the cyclopentadienyl ring. And for those of you that might recognize this from a chapter on aromaticity, the CP ring or CP anion is one of our classic aromatic anions. And it's because on the simplified structure here, we can draw resonance structures where that negative charge sits on all 5 of the possible carbons. So sometimes we just abbreviate it as a circle with a minus in the middle to represent that that negative charge is really spread out over the whole system. And because we have a ring that has a Huckel number of electrons, where we have full conjugation, and it's flat, overall this will be an aromatic anion. And that really helps explain the pKa of cyclopentadiene, which has a pKa of about 16. And that's crazy low for a carbanion. So generally carbanions, remember, like things like methyl anion are 50, and molecules like benzene are like 43. So those are really high numbers compared to 16. And so that helps explain this wonderful stabilizing effect that you get out of aromaticity. So that's the first kind of set of resonance structures here in this very special anion developed by the Lambert lab. And so if we continue that, maybe what we'll do instead is just put that negative charge dotted all the way around with the negative in the middle here. And because each of these then have a carbonyl hanging off of them, each of these structures then can also delocalize that charge into the ester, just like where we started with. So this is delocalized up into that carbonyl. And so it turns out that there's a total of 10 different resonance structures where that positive charge can sit in these anions. So let me just draw this one out real big here. And so that negative charge can sit partially on each of these carbonyl oxygens and partially on each one of these carbon atoms. And so there's a total of 10 different atoms that can have that charge. And so that's pretty crazy. And because that charge then is so diffuse, and because we have 5 different resonance structures on oxygen, it turns out it's an incredibly stable anion. And that stability of that conjugate anion helps explain why we can have this organic acid that has such an incredibly low pKa. And it's a function not only of just having 10 resonance structures, but also having these very crucial aromatic resonance structures that really help out. All right, so if it's true for acids, it should also be true for bases. And so this amine shown here is also incredibly basic. And so instead of taking off H+, let's just put on H+ instead. And we can use any of these old nitrogens to do it. Oops. And so that looks all right, except that one doesn't really get us anywhere for pulling electrons out. So what we have to do now is go back and consider, is that going to be the most basic nitrogen or not? And this is one of these things that's kind of partially confusing about the starting material. And for those of you that want a review or more discussion on this, I have a whole separate video posted under fundamental concepts and acids and bases for amines. And there I talk about molecules like DMAP that have this same very property, where the most obvious nitrogen to protonate is actually not going to be the one that you want to protonate. So we're actually going to want to protonate down here on the DMAP scaffold. And so let's just consider this starting material a little bit differently. I'm just going to redraw it down here. And the key resonance structure here that we're going to want to consider is moving that nitrogen lone pair around, taking this double bond all the way over here, and then moving that double bond up onto nitrogen. And so this would be a resonance structure. Like so. And of course, this one is uphill in a sort of sense because we've gone from a neutral molecule to something that has, two charges on it. But I think that this helps us illustrate why the sort of top nitrogen, as is drawn here, ends up being the basic nitrogen. So when we go ahead and treat this with H+, we're actually going to want to use that nitrogen there. Now, a fun thing about this system is it's also going to be aromatic. And so if we move this double bond up, we can put that positive charge here. And now if you count very carefully, we have a three-membered ring. So triangles by definition have to be a plane. It has 2 electrons in that ring, and it's fully conjugated. And so this is actually going to be an aromatic cation. So the cyclopropenyl cation has a Huckel number of electrons. And we can take that positive charge and we can move it around to every spot on this triangle. And then we can move it again if we really want to. Oops. And so we can put that positive charge on all 3 carbons. Furthermore, we can put it on any of the 3 nitrogens. So we could take the N lone pair here and move that down. Or we can put it on this nitrogen if we want to. And so all in all, there are going to be 6 different resonance structures for this particular protonated intermediate. Where that positive charge can sit on any of the 3 nitrogens or any of the 3 carbons, and that carbon structures are aromatic. So overall, that gives this cation a lot of place to put the charge, and it's also not as unstable as it normally would be because of the driving force of aromaticity. And so all in all, that helps explain why this organic molecule is a super good base, much better than it should be based on the pK of a mere amine. So with that, hopefully you've enjoyed this discussion, not only about resonance structures, but also a good reminder about some unusual aromatic cations, as well as a brief glance into the modern chemical literature. These are not old papers by any means, and so I think that they're really illustrative of some of the really fun concepts that you can unlock by being a true master of organic chemistry. And I'd put the Lambert Lab right up there with the best. All right, so hopefully you've enjoyed this Professor Carbon video. Please do subscribe to our YouTube channel. Also feel free to become a patron subscriber if you want access to the PDFs of these either before or after they're filled out. With that, thank you. Please tell a friend and watch the next video.